All right, this is number 35. Oh, I'm sorry, it's number 39. Number 39 on page 310. And in this problem, you're probably again wondering, why is this in the quadratic equation unit? These are radicals in this equation. So obviously something's going to happen probably to make this quadratic after we simplify uh, the expression and clear the denominator. So I notice I have a fraction with root x, x minus 4 in the denominator. So if I really want to write all of these over the lowest common denominator, I need to beef them up. So if the LCD is the square root of x minus 4, this term is already over it. To write this term over it, I have to multiply by 1 in the form of x minus 4 root x minus 4 times, over the square root of x minus 4. So that's a big fat 1 right there. And then this 1 is not over the square root of x minus 4, so that has to be multiplied by 1 in the form of root x minus 4 over root x minus 4. Okay, so now everything's over the square root of x minus 4 over the square root of x minus 4, so I can clear the denominators by multiplying every term on both sides by the lowest common denominator, and those will go away. So now in the numerator, I have root x minus 4 times root x minus 4, which is, by definition, x minus 4. The square root of something times the square root of the same thing is that thing, minus 2 equals the square root of x minus 4. Okay, so we've already previously learned, I'm going to simplify this to be x minus 6 equals the square root of x minus 4, that we want to isolate this expression and then raise both sides to the nth power. So this is a square root, so I will wrap and square both sides. Then I have on the left x squared minus 6x minus 6x, so negative minus 12x plus 36 equals x minus 4. Okay, so it's a quadratic equation. I'll get it in standard form. Actually, I'm going to subtract x from both sides. So minus 13x. Well, no, I'll just go ahead and add 4. Okay, now I can't factor actually I can. It factors to 8 and 5. So I think I'll go ahead and do that. It doesn't say, does it say I have to complete the square? It does not say I have to complete the square on this, and it is factorable. I can see pretty easily that this factors to be x minus 8 times x minus 5. So my initial solutions are a 5 and an 8, and I'm going to check them both in the original equation. So when I check 5, the square root of 5 minus 4 minus 2 over the square root of 5 minus 4 equals 1. The square root of 5 minus 4 is the square root of 1, which is 1. 1 minus 2 over 1, which is 2, does not equal 1. So negative 1 does not equal positive 1. So that one doesn't work, so I have to reject the 5. And then I'll try 8. So when I check 8, this is 8 minus 4 minus 2 over root 8 minus 4 equals 1. So the square root of 8 minus 4 is the square root of 4, which is 2, minus 2 over 2, which is 1, equals 1. And then we have it positive 1 does equal positive 1. So the 8 works. Okay. However, I could have also, instead of factoring right here, I could have used completing the square. So I'm going to show that in case you did that. We would start with x squared minus 13x plus blank to complete the square equals negative 40 plus blank to complete the square. So I would take negative 13 halves, and when I square that I get 169 over 4 when I square 13 halves here. So I have to combine a negative 40 with 169 fourths, so this is negative 160 fourths, the 40. So 169 minus 160 leaves 9 fourths. Nice and convenient, both numerator and denominator perfect squares. So I get x minus 13 halves when I take the square to the left is equal to the positive and negative square root of 9/4, which we can see is going to be 3 halves. So I'm going to add the 13 halves to both sides. I get x is 13 halves plus or minus 3 halves. So 13 halves plus 3 halves is 16 halves, or 8, which we got here. And 13 halves minus 3 halves is 10 halves, or 5, which we got here, and we already know has to be rejected. So that would have been an alternative way to do this one, but it didn't say that you had to use completing the square. So that is number 39.